In this video, we compare the sizes of two fundamental sigma-algebras on the real line. The Borel sigma-algebra is generated from the open sets by closing under complements and countable unions. The sigma-algebra of Lebesgue-measurable sets is obtained by extending the Borel algebra in a measure-theoretically natural way. Both collections are infinite, but their infinities are dramatically different. We will first see that the Borel sigma-algebra, despite its intricate infinite construction, contains exactly continuum many sets, the same cardinality as the real line itself. We will then discover that the Lebesgue-measurable sets are vastly larger. There are as many of them as there are arbitrary subsets of the reals. Finally, we close with a brief reflection on the axiom of choice and what mathematical existence really means. Part 1 is about the Borel sets and their textbook abstract definitions. They are usually introduced in one of three equivalent ways. First, as the sigma-algebra generated by the open sets. Second, as the sigma-algebra generated by the topology of the real line. Third, as the sigma-algebra generated by the open intervals. These definitions are ideal for proofs, but they conceal the actual construction of Borel sets. We will instead use an equivalent operational approach that begins with open intervals having rational endpoints. Here is the key technical simplification. We replace the uncountable family of all open intervals by a countable basis built from rational endpoints. Because the rationals are dense in the reals, every open interval can be written as a countable union of smaller open intervals with rational endpoints. You can picture this by choosing a sequence of rationals approaching the left endpoint from above and another sequence approaching the right endpoint from below. This gives a clean formula. The interval is the union of those rational subintervals. Now define J sub Q to be the set of all open intervals with rational endpoints. Each such interval is determined by a pair of rationals, so J sub Q injects into Q cross Q and is therefore countable. So we can enumerate it as I1, I2, I3, and so on. This countable list will be the raw material from which we build all Borel sets. Now we switch from an abstract definition to an operational recipe. We start from the countable rational basis, and we call it F0. From any family Fi, we generate the next family Fi plus 1 using two operators. Sigma produces all possible countable unions of elements of Fi. Comp takes complements of every set in Fr. Here is the formal definition of sigma of Fi. And here is the formal definition of comp of Fi. The recursive step is Fi plus 1 equals sigma of Fi union, comp of Fi. We now collect everything built at each finite stage of the construction. We define F as the union of all families Fi from I equals 0 to infinity. This already contains every set obtained by finitely many applications of our operators. However, this union alone is not yet closed under all countable unions. To complete the construction, we allow one additional step. After infinitely many stages, we gather everything built so far and continue applying the same rules. With this rule, the resulting family is closed under complements and countable unions. Therefore, the final family is a sigma-algebra containing the rational interval basis. By definition, this sigma-algebra is exactly the Borel sigma-algebra on the real line. Now we introduce the coding idea. We represent Borel sets by sequences of natural numbers. The goal is simple. Every Borel set should have a code. We proceed step by step, starting from the basic rational intervals. Our basis is countable. JQ equals J1, J2, J3, and so on. Each basic interval already has a natural number label, its index n. So we represent each basis element by an infinite sequence. For example, the code for Jn starts with 0, then n, and then zeros forever. Keep this pattern in mind. A 0 prefix tells us what kind of object we are coding. Now we encode the complement operator. This is the simplest operator on codes. Assume a Borel set A is already represented by a code sequence of natural numbers. To encode the complement, we prefix the sequence by a 1. So the code starting with 1 represents a complement. Now we consider a countable family of Borel sets. Call them A1, A2, A3, and so on. Each AI is already encoded as a sequence of natural numbers. Fix the index I, then the superscript j runs along the code sequence. In the next step, we will merge all these rows into one single code for the union. Now we encode a countable union as one single sequence of natural numbers. Assume we already have codes for A1, A2, A3, and so on. Place these codes as rows of an infinite table. On screen we only show a small 6x6 window. To build the code for the union, we enumerate this table diagonally. We start with a 1 superscript 1, then a 1 superscript 2, then a 2 superscript 1. Next we move to the next diagonal, a 3 superscript 1, then a 2 superscript 2, then a 1 superscript 3, and so on. The resulting code starts with 2, and then lists all these entries in that diagonal order. This new sequence is the code of sigma of the family, the countable union. Let us now connect the operator construction with the coding. We start from f0, the rational basis. Each basic interval already has a natural number label. Then, from a given stage, fi, we constructed codes for complements and for countable unions. So every stage fi is equivalent to a collection of codes that are sequences of natural numbers. Therefore, the full family F, defined as the union of all stages fi, is itself equivalent to a collection of sequences of natural numbers. In other words, we obtain an injection from f into n to the n. Now we can determine the cardinality of the Borel sigma algebra. From the coding construction, we get an injection into n to the n, so the Borel sets are at most continuum many. For the lower bound, every real number gives a singleton, and all singletons are Borel. So the Borel algebra has at least continuum many sets. Combining both inequalities, the Borel sigma algebra has exactly continuum many sets. Part 2. We now determine the cardinality of the Lebesgue-measurable sets. Step 1. We introduce the Cantor set AC. It is Borel, hence Lebesgue-measurable. It has measure 0, and it is uncountable. Step 2. We explain why C has continuum many points. In ternary representation, points in C use only the digits 0 and 2. Step 3. Every subset of a null measure set is Lebesgue-measurable with measure null. We will not prove this here. Therefore, all subsets of C are Lebesgue-measurable, so there are at least 2 to the Aleph, 0 Lebesgue-measurable sets. The Cantor set is constructed by starting with the unit interval and repeatedly removing middle thirds. Stage 0 is simply C sub 0 equals the closed interval from 0 to 1. At stage 1 we remove the open middle third, leaving 2 closed intervals of length 1/3 each. At stage 2 we remove the open middle third of each remaining interval, and so on. We continue this process indefinitely. At each stage the total length of the remaining set is multiplied by 2/3, and therefore shrinks towards 0. The Cantor set is defined as the intersection of all these stages. It is a null measure Borel set. We now show that the Cantor set has the same cardinality as the real line. In base 3, every x in the interval from 0 to 1 can be written as x equals 0 point followed by ternary digits, each digit being 0, 1, or 2. Terminating ternary expansions are not unique. For example, 0.020000 and so on equals 0.012222 and so on. After the first removal step, the remaining set, C1, is the left third and the right third, exactly the points whose first ternary digit is 0 or 2. After the second step, the remaining set, C2, consists of 4 intervals. Their first 2 ternary digits are 00, 02, 20, or 22. After the third step, the remaining set, C3, consists of 8 intervals. The first 3 ternary digits are all in the set 0 or 2. Therefore, a point lies in the Cantor set if and only if it has a ternary expansion with no digit 1 anywhere. so C is equivalent to the set of infinite sequences of zeros and twos. That is the same size as the real line. In particular, the Cantor set has cardinality 2 to the Aleph 0. First, the Cantor set C is Borel, hence Lebesgue-measurable, and its Lebesgue measure is 0. Second, Lebesgue measure is complete. If n is measurable with measure 0, then every of its subsets is also measurable, and still has measure 0. We will not prove this here. Now consider the power set P of C, the set of all subsets of C. By completeness, every A contained in C is Lebesgue-measurable. Since C has the size of the continuum, the power set P of C has cardinality 2 to the power 2 to the Aleph 0. Therefore P of C is contained in M of R, so the sigma-algebra of Lebesgue-measurable sets contains at least 2 to the power 2 to the Aleph 0 sets. We can now summarize the situation on the real line in one picture. The Borel sets sit inside the Lebesgue-measurable sets, which sit inside the full power set of the reals. In Part 1, we proved that the Borel sigma-algebra has size 2 to the Aleph 0. In Part 2, we proved that the Lebesgue-measurable sets have size 2 to the power 2 to the Aleph 0. Of course, every measurable set is a subset of the reals, so the measurable sets are, at most, as many as all subsets. That is the trivial upper bound. To show that the inclusion is strict, one must use the axiom of choice. A classical example is a Vitali set, a subset of the reals that is not Lebesgue-measurable. In this short outro, we look at the role of the axiom of choice in the measure problem. The strictness of the inclusion from M of R into 2 to the R is proved by using the axiom of choice. What we get is an existence theorem, not an explicit construction. It guarantees the existence of objects like Vitali sets. At this boundary, cartographers once wrote, "Here be dragons." Solovay showed that, relative to standard consistency assumptions, there is a model in which every set of real numbers is Lebesgue-measurable. Without the full axiom of choice, the strictness cannot be proved in general. In such a universe, the middle box disappears. The measurable sets coincide with the full power set of the reals. Does the Vitali set then cease to exist? No. It never existed, absolutely. In mathematics, existing only means derivable from the chosen axioms. Choice gives existence by decree. Emile Borel asked for existence by definition.